Welcome to the New Books Network.
Hello, welcome to New Books in Neuroscience. This is a podcast channel with the New Books Network. I am Dr. John Griffiths from the University of Toronto and Toronto Centre for Addiction and Mental Health, and I'm co-host to this channel with Joseph Friedman and Sophie Barwich, Victoria Reedman, and Chris Harris. And today I'm speaking with Professor Robert or Bob Stickold. So Dr. Stickold is a full professor in the Department of Psychiatry at Harvard Medical School and the Beth Israel Deaconess Medical Center in Boston. And for several decades now, he's been a leader in the field of sleep research, specifically the cognitive neuroscience of sleep and dreaming. And he's made major contributions to our understanding, in particular, the role of sleep in memory consolidation. So Dr. Stickold has hundreds of scientific publications in this and other areas. And today we're going to be talking about his new book, which is called When Brains Dream, Exploring the Science and Mysteries of Sleep, which he's written together with Dr. Antonio Tony Zadra from the University of Montreal. When Brains Dream is a fascinating summary of the history and current state of the art of the science of dreams. It's a really engaging book. It really gives the reader a sense for how psychological and neuroscientific dream research is done by scientists in the lab. And it's also crystal clear about the fairly muddy topic of what we can and what we can't say about what we know about the causes and the mechanisms and functions of sleep and dreaming. So, Bob, welcome to New Books in Neuroscience.
I'm delighted to be here. Thank you.
Yep, you're very welcome. So what's customary for these discussions is I like to begin with some background on the authors. So if you could tell us a little bit about your professional biography, basically how you got into this research field and what was the trajectory that led you to writing with Tony, to you and Tony writing When Brains Dream.
Well, I have a very circuitous path getting here. I actually have a PhD in biochemistry, did my doctoral thesis research on DNA replication in bacteria. And it's been a long and tortuous route from biochemistry to neurochemistry to neurophysiology, and then finally into sleep research. My interest in sleep actually originated around dreams, but then sort of turned and focused mostly for the last 25 years on the role of sleep in memory processing. And Tony and I got together because Tony wanted to write an article for some yet to be determined scientific journal on the myths of dreaming, because there's all these myths that surround dreaming that even scientists, even sleep researchers tend to believe, such as the idea that dreaming only occurs in REM sleep. And so he wanted to write this article to debunk these myths. And as we talked about it more and more, we realized we had way too much to say for an article, and it just expanded into a book.
That's fascinating. So, and have you guys been working together for a long time?
So Tony and I never worked together before this. Tony came to me with this idea, and we met at the annual sleep meetings, which were in Boston, I guess 2.5 years ago now. And that's the first time we seriously started thinking about working together. And it was quite enjoyable, because when we started, we had no idea about each other's writing styles even. And we're delighted to find that we couldn't even tell which of us wrote which chapters. Our styles are so similar. But our work together has really been limited to just working on this book so far.
That's really interesting that that's a relatively new collaboration, because one of the nice touches in the writing style, basically the book is back and forth between a little bit about, basically you kind of refer to yourselves in the first person. So you say like Bob, has worked on, knows about, understands, has been talking with his daughter about this, Tony, It kind of sounds like you're long-term friends, the way it comes across in the book.
Well, now we are.
Right, yeah. And so, and in terms of like professional expertise, would you say? Because I think if I'm reading things correctly from your respective bodies of work, Tony's coming at the question of the study of sleep and dreaming from a little bit more of a experimental psychology line, and you are maybe more a kind of clinical psychiatry / neurophysiology scientist. Is that a reasonable summary?
No, that's exactly right. I describe myself as a cognitive neuroscientist, but I spent 4 years working with Steve Kufler at Harvard Medical School, poking, ganglion cells in bullfrogs and in mud puppies and doing intracellular recording. So I have my bona fides in neurophysiology, and so I come at it really from this really hard science perspective.
Right. And did you trained with Alan Hobson? Did you? Is that correct, or is that you worked with him
So
a fair bit as
I
well?
did Yeah. After I finished postdocing, I was an assistant professor at the University of Massachusetts Medical Center for 3 years, and then actually left that job in sort of dissatisfaction with what I was doing, and then started working with Alan Hobson back at Harvard Medical School. And we worked together for, I guess, a half dozen years, working on cognitive neuroscience of sleep.
Cognitive neuroscience, but I guess also your biochemist background comes into play somewhat in the more of the neurochemistry of sleep, and particularly of dreaming as well.
Well, my biochemistry background certainly helped me when I started thinking about neuromodulation in the brain. But its impact is even deeper, because I think it has instilled in me a higher standard scientifically in terms of what kind of evidence, what kind of data is convincing. I feel like I come at it more like a neuroscientist than like an experimental psychologist. And it really, I think, increases the rigor of the work I've been able to do over the last 25 years.
Yeah, that's good. I think it's reasonable to say we can aspire to the standards of chemistry in cognitive neuroscience. I would sign up to that. Okay, so let's go ahead and dive into the book. So there's a variety of fascinating things that you cover in the book. There's the neurobiology of sleep and dreaming. There's a lot on memory coming from your own expertise. You touch on consciousness. There's medical applications, all that good stuff. I'd like to get into the kind of current status of knowledge in various areas in a little bit, but as is to be expected, really, in this type of book, you open up with the history in the first few chapters. So, I was wondering if you could take us through that. One of the things that you touch on, and that I noted in your opening 1 to 2 chapters, is the discussion of Freud. So Freud is like the elephant in the room in any summary of understanding of sleep, and there's an elephant in more than one way, I guess. And it's what I find interesting was that it's common in things like Psychology 101 courses to do sometimes a fairly brutal takedown of Freudian ideas, but also maybe with a begrudging acknowledgement that there's important contributions to things like understanding of unconscious thought processes and so on. And you actually do something like that, but actually specifically in the area of sleep, as in you play down basically the originality of some of Freud's contributions that I think are generally considered to be, new ideas injected by him in 1905 or whatever. So maybe you could take us through a little bit of that early history, and then we can go from there through into the 20th century history of sleep research, and then we'll bring it up to the present day.
Great. So it's absolutely true that from 1900 to the mid-1970s, at least, all dream theory revolved around Freud. He was a superb marketer in the end of his dream theories, and cheerfully claimed credit not only for his own work, but actually for work that many others had done over the previous 50 years. So So the real start of scientific dream research goes back to around the 1860s. And as an example, there was a book by a guy named Saint Denis, The Dreams and the Way to Guide Them. That is a beautiful experimental and theoretical discussion of dreaming. So from the experimental point of view, he wanted to know how associations contributed to dreaming and how sensory stimulation during sleep might contribute. And he set up this project. He did a lot of traveling around France. And when he went to a new city, he would always buy a new perfume and spray it onto his hands and smell it frequently the whole time that he was in that town. And he would do that across France over an extended period until he had 10 or 20 different perfumes from 10 or 20 different cities. And then he would have his servant, and I love that he had servants, on some nights when he was sleeping, spray one of these perfumes at him while he was sleeping, and then a few minutes later wake him up and collect the dream report. And he was able to determine that when this happened, he would have dreams that did not incorporate the perfume, that he was not aware of the perfume having been sprayed, but would actually have a dream that took place in that town or city where he had been exposed to that perfume previously. He did it with music. He would go to big parties, and he would ask the orchestra, the band, to play a particular song while he danced with one woman, and then a different song while he danced with another woman, and then have his servant play record recordings of one or the other of those songs while he was sleeping, and see incorporation of the appropriate woman into his dreams. So he was able to show both that the sensory stimulation during sleep can get into your brain and into your mind, if you will, and that your brain in constructing dreams could follow associative links to the person or place associated with the music or the smell. And he actually came up with these two concepts, one of which he called abstraction, where he argued that a sensory input during the day, like an orange, could in a dream reappear as a beach ball having the same shape, or an orange sunset having the same color, or even a lemon grove having the same general smells. And so he called this abstraction, and he came up with a similar concept where sometimes he would spray two perfumes at night, or his servant would, and he would have a dream that seemed to meld together those two locations. And so he came up with this concept of, what did he call it? The combination of images. And these exactly predicted Freud's concepts of displacement and condensation. And Freud acknowledges that he read Saint Denis's book, but doesn't point out that Denis had come up with these very same common concepts. So there was some nice experimental psychology and theoretical work 45 years before Freud's book came out. Mary Calkin, who was a professor at Wellesley College here in Massachusetts, in 1893 put out a paper in the American Journal of Psychology entitled Statistics of Dreams, where she analyzed 400 dream reports, about 20 times more than you'll find in Freud's interpretation of dreams, and showed things, for example, like that dreams are longer and more vivid later in the night, which we now know is when we have most of our REM sleep, and those dreams are, in fact, longer and more vivid. So all of this research was done and had been read by Freud before he wrote his interpretation of dreams, which was published in 1899, but given a publication date of 1900, so it could be seen as into the next century. And Freud's work was a brilliant piece of literature. It was very well written. In fact, one of Freud's big complaints later in his life is that while he won literary awards, he never won a scientific award. And the reason is because the book isn't scientific. It's a literary wandering through the question of dreaming. But it was so powerful in the way it was written that it really dominated all discussion about dreaming until the mid-1970s. And that's when Alan Hobson and Bob McCarley, then both at Harvard Medical School, published a pair of articles in the American Journal of Psychiatry where they introduced their activation synthesis model. And it was a direct anti-Freudian rejection of Freud's arguments. And they said that dream construction is a process of brain activation followed by synthesis. And the activation is, they said, the dreaming is triggered by the largely random firing of giant neurons in the pontine reticular formation. And that this activity in the pons sent up waves of activity to the lateral geniculate nucleus that were propagated onto the visual cortex, producing a self-generated and auto-generated visual sensation in the brain. And at that point, the synthesis part of activation synthesis took over. And in synthesis, the forebrain, they said, was making the best of a bad job. And I'm quoting him here. Best of a bad job in producing partially coherent dream imagery from the relatively noisy signals sent up to it from the brainstem. And it led people to interpret their model as saying that dreams are random. And if you read the article carefully, that's not actually what they say. I mean, they specifically say in the article that dreams have psychological content, that they're made from our own memories, and that they have meaning associated with what content is used in that synthesis process. But the notion that the origin of the dreams was in random activity in the brainstem as opposed to suppressed or repressed wishes in the unconscious just freaked out the entire psychoanalytic community. And Hobson loved that. He loved the reaction he got. And really, for the next 50 years, he dropped any discussion of the synthesis half of the model and really focused on the activation portion and how it argued against Freud's models of dreams being initiated by these repressed desires. And so then that sort of got a lot of press. And yes, psychology textbooks started saying that the current models say that dreams are random and meaningless. And Hobson and McCarley were happy with that. They were satisfied with that, even though Hobson clearly didn't believe that they were either random or meaningless. But that then sort of became the dominant view and has been probably for the next 25 years. And since then, sort of cognitive neuroscientists, experimental psychologists have begun taking it back and saying, no, obviously our dreams are anything but random. They obviously relate to events in our lives and memories from our lives in a at least somewhat coherent manner. And then with this book, When Brains Dream, we try to pull together a model of dreaming that takes what we've learned over the last 25 years about sleep's role in memory processing and what that same period has given us in terms of better understanding of the content of dreams and the differences in dreams across different sleep stages, across different brain states, to come up with a new model to help us understand the mechanisms and the functions of dreaming.
That's fantastic. That was a roller coaster ride straight through from 1850 up to present day, and the and great job. And the model that you to propose in the book, the next up model, I want to come to that shortly. But first, maybe just develop a little bit more the neurobiology that you were summarizing just now. And I had a few questions from what you just said. So firstly, is it you were indicating that it was the synthesis part was from the activation synthesis model. The cognitive component, and if you like, the piece of the dreaming process that maybe speaks to what Freudian and other psychoanalytic dream theories are maybe interested in cashing out. That's in the synthesis part of the activation synthesis model. Is that reasonable to say? And I ask that actually because
that's correct. That's correct.
Yeah. I do recall reading
and I just want to say,
from. Sorry, go ahead.
I was just going to say that the relevance of the activation piece to the synthesis piece is rather it's sort of cross-dimensional. It's sort of like if you try to figure out what a car is and what its purpose is, and you talk a lot about the starter motor, and all the starter motor is it's an electrical motor that turns a small gear that in turn causes the flywheel of the engine to slowly rotate and in fact start to produce enough electricity to get the engine firing. And after that, you can take that starter and take it out of the car and throw it away, and you can drive around just fine. So it's important to understand from one perspective how you get a car started with a starter motor, in the old days with a crank, literally. But it's really, in the end, sort of irrelevant to what the car does. And I think the same is true with activation synthesis. I mean, I think it's fascinating to talk about where does the brain get the initial stimulation that starts its process of narrative construction, of dream construction. But once that process is begun, it's sort of not relevant to the synthesis part, which is why it's a shame that Hobson chose to ignore that synthesis part for so long.
Right. And and that it's interesting that you put it together that way, because the point I was just going to reflect on was I've seen, I don't know if it's a robust claim, that I've seen descriptions or proposals of alternative sources of the ascending arousal activation coming maybe from basal ganglia and like quote unquote motivational systems, as opposed to the brainstem, and that potentially having, this is from Mark Soames and others, but the source of the ascending arousal being significant with respect to Freudian dream interpretation if it's coming from a basal ganglia, quasi motivational system, as opposed to the completely dumb spinal cord, for want of a better way of describing it.
Well, the spinal cord would object to that characterization. But right, I mean, we're talking about, so that brainstem activation that comes up and activates the visual cortex also activates the amygdala. So that can also be a source of emotional activation in that process. And yes, as coming from the basal ganglia, you might be getting some activation that's dopaminergic that would be more towards motivation. But in all of these cases, it's content free, right? There's nothing in the basal ganglia that will bring up memories of your mother. There's nothing in there that'll bring up memories of forbidden desires. It would just bring up dopaminergic activation. And that's really what Soames is saying. And I say, great, dopaminergic activation, amygdala activation, visual cortical activation, put all that into the mix, and then ask the brain to, crank that engine over and start a construction process. But the question is, where does it look to create that dream? And it's clear that it starts with memories from the day, that in almost all cases, dreams, if you look at them hard enough and try to look at them objectively, seem to have at least some sources that come from memories of events from the day. So that's probably from the synthesis point of view where it starts.
Right. So let's move on to synthesis and memories and cortical systems. But I have one other question on the ascending part. It's kind of in between, really. You got to some of the spirit of it when you're saying, it's all just activation coming from lower ascending systems. But another feature of those ascending systems is they have the 4 or 5 of them have their own particular neurochemical flavor, right? We have the serotonergic system, dopaminergic system, cholinergic system, etc. And actually, the last book that I did read on dreams before yours was The Dream Drugstore by J. Allen Hobson, and this is also a kind of caricature of psychiatry, right? Is like brain as vat of chemicals. That's in a sense that's kind of how psychiatry thinks about the brain. So, but that would be a version of what you were saying about not thinking about the cognitive and representational content of the cortex yet, but just thinking about what's special about the neurochemical state of the brain in dreaming, as opposed to waking and slow wave sleep, and how does that relate to the function of those ascending neuromodulatory systems?
Right. So the neuromodulation of the brain goes through dramatic changes as we first fall asleep, and as we then cycle through REM, rapid eye movement sleep, and non-REM sleep. When we go into sleep, all of those neuromodulatory systems, dopaminergic, cholinergic, noradrenergic, serotonergic, they all quiet down. If you look in rats with perfusion studies, the rate of release of those chemicals is decreased as you go into early non-REM sleep. And then when you go into REM sleep, you get this really quite phenomenal shift. Release of serotonin from the raphe, release of noradrenaline. Both of those are completely shut off during REM sleep. And at the same time, the release of acetylcholine skyrockets. So that release of acetylcholine, for example, in the hippocampus is higher during REM sleep than during waking. And this suggests the importance of REM sleep for memory processing. We know that if you give a muscarinic cholinergic blocker to someone when they're awake, they can't form new memories. They can recall memories just fine, but they can't encode new information. So that acetylcholine shift from low in non-REM to high in REM is clearly going to be contributing to a lot of the memory processing effects that we see in sleep. There's more subtle things as well. When you shut off noradrenaline, norepinephrine, you shift the brain into a state where cognitively, psychologically, it's biased towards weaker associations as opposed to strong ones. We did studies back in 1999, 2000, where we would wake people up from either light non-REM sleep or from REM sleep, and then very quickly, literally in 2 to 3 minutes, put them through a semantic priming test, which is a cognitive psychological test of associative memory strengths. And we're able to show that when you wake someone up from REM sleep, the speed at which they can make an association, for example, from thief to wrong, is faster than for a canonically strong association like right, wrong. So the brain is now biased towards searching for and activating these weaker associations, which is a characteristic, especially of REM sleep dreaming, where you have all these bizarre events happening that seem sort of very weakly connected to what's going on, but only just so. You also see changes in information flow in the brain. When you go into slow wave sleep, the deeper portions of REM sleep, you find that information flow tends to be from the hippocampus to the cortex, while flow from the cortex, neocortex, back to the hippocampus is pretty much shut down. And in REM sleep, that flips. So now you have lots of information flowing into the hippocampus, but almost nothing flowing out. And that's probably why when we dream, we never replay episodic memories. We had a paper out again around 2000 where we show that when people can identify or believe strongly that they can identify the waking sources of some dream element, it's never, and never means no more than 3 cases out of 399. It never seems to actually replay the episodic memory that the dreamer identifies as the source of that dream element. So that shutdown of flow out of the hippocampus probably plays a critical role in blocking that episodic replay. And you've got a very, very strong shutdown of dorsolateral prefrontal cortex, which of course is involved in executive decision making and logic and reasoning and impulse control. And if you take those things and put them together, what you get is a kind of thinking, if you will, that's very different than you see when a person is awake. So when you're awake, you tend to look at strong associations to recent events and think about them. And you think about that event by replaying that episodic memory while you're considering the association. And your frontal cortex is throwing a lot of them out as irrelevant or irrational or illogical. And all of those constraints are gone when you dream. When you're dreaming, you only have that associative network in neocortical regions available for the constructing of a dream. It does it by looking at weak associations, and it does it without frontal inhibition. Oh, and by the way, the limbic system is cranked up during REM sleep, all along that midline structures, the amygdala, the medial orbital frontal cortex. These regions are all more activated than during wake. And so it sets you up for sort of bizarre, hyperassociative, emotional, unchecked kind of cognition that we call dreaming.
Right. So we have the. I mean, it's fascinating that you really go from the chemical synaptic level right up to the cognitive level and all of the systems, the systems neurophysiology in between, in pulling together that picture. I mean, just to kind of paraphrase, so you had the basically kind of gain control change with the noradrenaline drop. You have the let's say memory or plasticity switch or modulation with the cholinergic changes, and then you have all of these activation of frontal and medial hippocampal and amygdala systems doing like systems level changes in addition to a probably profoundly different neurochemical state that a given neuron is experiencing during the dreaming part of sleep. Do you have a
right? And it's almost
a preference or for which of those, if you were to say, okay, either the phenomenology or just broadly speaking, the brain state of the dreaming brain is the neurochemical switch or the systems interaction switches? Do you have I don't know if you could kind of give them a weighting, like 50-50, 70-30, or would you just not answer that question, but out of principle?
Right. You're asking me which vitamin is the one that I really need to take if I want to be healthy.
I suppose I have.
The brain evolved. The brain evolved all of these regulatory modulations, all the neurochemical ones, all the connectivity ones, all the regional activation ones. They all evolved presumably to work in synergy. And we could try, if we had enough millions of dollars and dozens of years, to sort of go through phylogeny and try to figure out the order in which those things appeared. But I think taking away any one of them dampens both our ability to do memory processing during sleep and our ability to use dreaming in the service of that memory processing. So my background, I'm a biochemist by training, so I'll vote for the neuromodulators. But that's
Well,
because
that
it's
was
my
what I
own
was maybe
team.
getting at when I asked at the start. I was thinking that was something that maybe spoke to some of your early experience there.
Right. But
Okay, so
again, if you
maybe
didn't have
the other so your main scientific emphasis is in memory, and you've touched on that already. I have one other question on basically kind of brain state. Let's say before we go a little bit further into the specifics of the memory consolidation in sleep and dreaming, is let's call it, say, a neuroimaging perspective. So what does a dreaming brain, and let's say also a sleeping brain, so a brain in slow wave sleep or non-REM sleep and REM sleep, or dreaming and non-dreaming sleep, look like in the type of non-invasive imaging techniques that you use? So you work with EEG, you work with fMRI. You mentioned a little bit like certain bits light up, but could you give us a little kind of narrative summary of, if I'm looking at some brain imaging data, what do I see when the brain is dreaming?
Well, if you start by looking at the EEG, at the electrical activity of the brain, what you find is that as you fall asleep, you start to see a slowing down of the EEG. You start to pick up clear oscillations in frequency band of 10 or 12 hertz. And as you go deeper into non-REM sleep, those oscillations get larger and slower, so that by the time you get into slow wave sleep, which is the deepest stages of sleep, as its name suggests, you have these large 200 microvolt surface recording waves in the EEG that are running at about 1 to 4 hertz at slow speeds. And I sometimes describe it as sort of being outside an amphitheater where there's a football game going on, and hearing people clapping rhythmically together. You can't pick out the individual people, but since they're clapping in unison, you can pick it up even outside the brain as it is. And then as you go into REM sleep, the EEG becomes fast and desynchronized again and looks very much like the waking EEG. In fact, REM sleep was originally called paradoxical sleep because when they looked at the EEG, they thought that the subjects were awake while they were actually asleep. If you look with PET, positron emission tomography, what you see, first of all, is that when you go into slow wave sleep, into deep non-REM sleep, the whole brain quiets down. You have about a 40% reduction in glucose and oxygen consumption. And it's pretty uniform across the brain. And then as you come up into REM sleep, you start to see a divergence. You see some regions, like dorsolateral prefrontal cortex, where oxygen and glucose utilization drops even further, showing that they're becoming even less active. While other regions, and specifically the midline limbic system, frontal association cortices, the amygdala, these regions start to show increased levels of activation, some even beyond those that you see in waking, and the hippocampus also in REM sleep. So you see this shift towards quiet in slow wave sleep, and then actually increased activity regionally during REM sleep. With dreaming, we can't say much because we don't have a physiological measure of dreaming. Giulio Tononi in Wisconsin has done some studies where he has recorded high density EEG and then woken people up to find out when they are dreaming and when they aren't dreaming, and has found statistically at least that when people on awakening report that they were dreaming, they tend to show local decreases in those low frequency band oscillations in the EEG in posterior cortical regions. But beyond that, we don't really have good markers of when we dream.
Is the increase in the slow wave and the increase in the hippocampal activity, is there a good case for a causal relationship there? If there's a hippocampal theta delta rhythmic activity propagating up, or is that confusing things?
For dreaming?
Yeah.
Are you saying for dreaming?
No, I'm saying for slow wave.
They don't see it. They don't see it. Yeah. Causal is tricky because it's all correlational, right? What you want to do, and we can do that now, is we can use methods to increase slow wave sleep. Normally, it's sort of a global increase. We can do that pharmacologically, but we can do transcranial electrical stimulation to get local increases in slow wave activity, and then ask these questions. But no one has done that yet. We don't have experimental in the sense of causally aimed studies to look at what causes dreaming. And another issue is it might turn out that we're actually dreaming 75-80% of the night, and that not dreaming or not being able to recall any dreaming is the much less common state. So it might have to do more with regulation of the intensity of the dreaming or how easily those dreams are recalled on waking up.
Okay. So let's move over to memory full on now. So at some level, it's I guess it's obvious that it's probably been known to mankind for a long time that a good night's sleep helps with memory. It seems unlikely that was a 20th century discovery per se at a psychological level, but the real appreciation of the role of sleep and kind of unpacking the mechanisms of sleep in memory consolidation at all levels, at a neurochemical level, at a synaptic level, at a physiological level. This is something that really came through in part from your own work, as well as others in I guess, around the turn of the 21st century. Would that be reasonable to say that there was a big boost in the understanding of the role of memory consolidation in sleep around about that time, or would you locate it earlier?
No, it's right at that time, and I've got the graph of number of publications with sleep and memory in the title, and right around 2000, 2001, the curve just turns from pretty flat for the previous 50 years at a half dozen papers a year to the current rate, which is upwards of 400 papers a year. And, one thing that marked that inflection point was a review article that we had in Science on sleep, memory, and dreams. In the year 2000, every year Science has one issue that has a special section that's aimed for the timed for the neurosciences meeting. And in 2000, they decided to do that on sleep. And so the articles, had the cover of Science magazine. The booth at the Neuroscience Society meeting was giving out copies of that issue. And it suddenly gained attention and it gained focus. You commented that we've known for a long time that sleep obviously has something to do with memory. But mostly, I think, the concept was that if you hadn't had enough sleep, then the next day it's going to be hard to form memories, that sleep is important for the subsequent encoding of memories. And what we've learned over the last 20 years is that it's even more important for the memories that we formed the day before, for the memories encoded before we went to sleep. That probably all the memories that we form during the day are considered again during the night. And 200, 400, 2,000 papers now published on sleep and memory since the year 2000. And they all together basically say that every aspect of memory processing occurs while we sleep. Memories are stabilized so that they're resistant to interference. They're strengthened so that memories for how to perform tasks lead to better performance the day after than at the end of training itself. Sleep helps with the integration of new information into pre-existing cognitive memory networks. It helps with the extraction of gist from memories from the day before. It can discover rules in complex data sets that are perceived, experienced during the day. It can selectively decide to retain emotional components of an episodic memory while letting other aspects of that same memory be forgotten. All of this processing, all of this work to try to turn the memory into a more useful construct, one that will be more useful in one's future, seems to happen while we're sleeping.
One of the
and this process,
particularly compelling kind of phrases that I've heard that is, in a way, it's a little bit more general than what you were just describing. Is that, and I apologize, I don't know the correct attribution for this, but that sleep is the price we pay for the ability to learn, as in the and specifically there's this notion of the synaptic homeostasis hypothesis, as in like the ability to learn, which sometimes translates in neuroscience as neuroplasticity. Neuroplasticity is fundamentally requires, it appears, sleep-like processes in order to allow new memories to be formed.
Right. So Giulio Tononi and Chiara Tirelli have come up with this model of synaptic homeostasis, which argues that while we sleep, the brain does in their original model, a global downscaling of all synaptic strengths. The argument is you can't keep strengthening your synapses all the time, every day, all over the brain, or else you'll reach a point where the brain is functionally saturated and you go into an epileptic seizure because the brain just starts firing on its own. At some point, you reach a level of saturation where you have to downscale. And although there's little evidence that we actually are reaching that state after a single day, their argument was that you need to downscale synapses and that we do that while we sleep. And that's the synaptic homeostasis model. They've sort of modified it now because of pushback from people like me arguing that if, as they suggest, all synapses are downscaled by 20% every night, how do you keep memories for years without them being completely lost? So now it's a selective downscaling where only those recently strengthened synapses, which are in some way calculated to be unimportant, get downscaled. And that would fit in directly with everything else that people have been saying, just trying to provide a cellular mechanism. And whether it's actual strengthening of synaptic connections, and there is good evidence for that, or whether it's the absence of weakening of synaptic connections, I think it's undoubtedly a mixture of both of those. And the net result is not just a brain that's better able to learn again tomorrow, but a brain in which memories have clearly been modified over the course of the night. And Tononi's model really doesn't address that issue of the kinds of complex processing of memories that happens during the night. So that has to be a separate and parallel process. And they can both be important, just like the systems level changes in brain activity and the neuromodulatory changes are both necessary for this sleep-dependent memory processing and dreaming to occur. So I'm happy with the synaptic homeostasis as long as it's seen as part of the mechanisms that lead to improved memory across the night.
That's fascinating. I didn't know I didn't know you'd been having that dialogue. I should check out if you have some references you can point me to on that. It's an interesting conversation. And this actually leads to one of the things that I want to ask you about. And it for me, the single major thing that I really learned from reading the book is, and you kind of summarize this as something like a caricature argument, or like how people used to think about things, is that there's a lot more memory processing going on during dreaming than I think is maybe the textbook description. So I wanted to just follow that on from the discussion of the synaptic homeostasis, because I think the way that's been proposed at the cellular level really relates very strongly to the slow wave and to the up and down states, which is a feature of slow wave sleep, but not so much or not at all a feature of REM sleep. So, is the synaptic homeostasis model dependent, specifically a slow wave sleep phenomenon in your eyes or in Tononi's eyes, and does it extend to REM as well?
It does not extend to REM, and there have been these. He gave a talk at Harvard a few years back now, where he's talking about how sleep is the price the brain pays for synaptic homeostasis. And I asked him, well, what about REM sleep? Because there doesn't seem to be any of this homeostatic activity, any of this downscaling, any of these slow waves in REM sleep. And he responds, says, oh, I'm not talking about REM sleep. So, when Alan Hobson talks about dreaming, he says it's just REM sleep, really. And when Tononi talks about synaptic homeostasis, it's all non-REM, and it's mostly slow wave sleep. And it brings up the interesting question of why we have these different stages of sleep. And I've argued that we see in slow wave sleep different types of memory processing. Slow wave sleep is really good for that stabilization and consolidation of episodic memories, whereas all of these more complex types of abstraction and extraction of information from memories seems to correlate with REM sleep. It might be that you just need very different brain states if you want to optimize these different types of memories. I give the example of a task that shows a 20% overnight improvement is a task where you learn to type a sequence of keys on the keyboard, classically 41324, which you type over and over during training, and then at testing some hours later with or without intervening sleep. And you could imagine that the brain state that would optimize an enhancement of that performance capability would be very different from the brain state that would, say, selectively strengthen a particular episodic memory from the day before. And so maybe the brain just had to evolve these different brain states first for that stabilization and consolidation of episodic memories, because slow wave sleep came first evolutionarily. And then only much, much later does REM sleep appear and allow for more sophisticated abstraction of knowledge. And maybe we needed those two different brain states to do those two different types of memory processing.
Right. And we mentioned before the big boost in understanding and the record of it in the publication record and so on in 2000. So in the case of, could you put a rough date on whether there's been a similar realization or a similar kind of boost in terms of the understanding of the role of dreaming in memory consolidation? Or another way of saying this, as I said, what I think is the kind of caricature, simple textbook description is that memory consolidation is a slow wave sleep phenomenon. So how would you go about correcting the record on that? What would be, well, is that actually a correct kind of, as I said, caricature textbook description of how people broadly think about things? Has the thinking on that changed very recently, or has that been more or less the thinking for a while? Because to me, that, as I said, that was something that was relatively new to me when I was reading the book, is how much you really do know, and what you've learned from your work about dreaming in memory consolidation in particular, which I thought was really more understood in the context of slow wave sleep.
So it's interesting. For a long time, going back to the discovery of REM sleep in the 1950s, when people looked at those EEG differences, they saw the large slow waves of slow wave sleep and thought that that was a sign that the brain was basically inactive, because you also see that in people in coma. And in REM sleep, the brain's EEG looked very similar to waking. So for a long time, the assumption was that everything was really happening in REM sleep and not in slow wave sleep. And somewhere around, I'm guessing now, but probably around 2010, people started looking at types of memory which are clearly correlated with slow wave sleep. And the most classic example is word pairs, where you train people to memorize a list of 20 or 40 word pairs, where I give you the first word and you can recall the second one. And that became a dominant experimental paradigm. And since that one turns out to depend on slow wave sleep, they really developed this view, this general consensus that slow wave sleep was what's important. But I don't think there's any real evidence for that slow wave sleep is more important, for example, than lighter non-REM sleep or REM sleep, that they each seem to be involved in a different type of memory processing. And so depending on what kind of memory you're interested in, you find one state of sleep or another to be the really important one. If you're looking at people with memory deficits, if you're looking at elderly people, if you're looking at Alzheimer patients, those are all disruptions of episodic memory. And so that slow wave sleep becomes correctly the focus of attention. Plus, we now have sleep spindles, which are seen in non-REM sleep, but not REM sleep, which are these 1 second long bursts of synchronized activity at about 10 to 16 hertz, which are known to be involved in memory consolidation. They cause a burst of increase in calcium influx into neurons. We can experimentally manipulate them and cause greater or lesser memory consolidation across the night. So if you want to be looking at cellular and small network scale markers and mechanisms for memory processing during sleep, then you're going to be focusing again on non-REM sleep. So I think it's sort of like where the spotlight is shining is where people go and look. But I think I think if I pushed any researcher in the field, they would agree that REM sleep is equally important to that memory processing that occurs during sleep.
Okay, good. And I think it's probably always the case that how you just described it's that it's complicated when you drill down. So one of the things you do in the book, and I gather this is probably one of the intellectual fruits of your collaboration with Tony, was this model that you have now called Next Up, which stands for Network Exploration, and actually I forget the rest of it, which characterizes some of these features, some of the role of these different sleep processes in different types of memory. So did you want to talk us through the Next Up model and how that kind of synthesizes the different parts of the puzzle for you?
Sure. One of the fascinating things about dream research is that there has been almost no consideration of the function of dreaming. Freud actually thought that the function of dreaming was to prevent memory processing. It was to prevent those memories of repressed, suppressed desires from coming into the brain and being processed. But there's been very little discussion of that. And it tends to be along the line of, well, it helps your brain think about emotional issues, but not even to process them necessarily. So it's been an area that's perhaps not that different from where sleep research was at the start of the 21st century. Right at the end of the 20th century, Alan Hobson was famously quoted as saying that the only known function of sleep was to cure sleepiness. So, even as recently as 2000, we really didn't have anything much to say about why we slept, what the function of sleeping was. I mean, it was supposed to let the brain rest, but why more than just lying quietly? So we really didn't have studies that were looking at the function of sleep. And the same is true for dreaming, and that extends even to the present day, really. So in writing this book, Tony and I chose to put together a model that can arguably explain both the mechanism of dream construction and its function. And next up, the name of the model stands for Network Exploration to Understand Possibilities. And the argument is that when we dream, what the brain is doing is it's recalling memories of events from the day, memories that have in some way been tagged during that waking period as important and unfinished memories, or memories of important and unfinished concepts or concerns or events. And it takes those tagged memories and it starts looking for associations to them that are more or less distant, and less distant in non-REM sleep and more distant in REM sleep. In REM sleep, specifically looking for distant, weak associations. And the brain then analyzes whether this association is useful, is one that should be strengthened and made available for one's subsequent waking life. It's not that different from what we do when we're awake, except for the fact that it's looking at these more unexpected, these more distant, these weaker associations. And it's doing it without the filtering of the frontal cortex that would tend to reject most, if not all of these as irrelevant. And then the issue of what dreaming is about is how the brain goes about testing these newly discovered associations. And the method it uses is to create a narrative, a story, if you will, that plays out in real time and plays out within our conscious awareness. And what's fascinating about it is it's exactly what we do when we're awake. If you decide that you're going to try to catch this seminar this afternoon, but the timing is kind of tight, what you do is you imagine the process of getting there. You say to yourself, well, okay, I'm going to have to leave early, which means I'm going to have to get out of this meeting early. So I should warn people at the start of the meeting. And then you sort of imagine yourself doing that. You imagine yourself, am I going to take the car? I'm going to take the bus. I'm going to try to walk there. How am I going to get there? How long does that seminar go? At the end of the seminar, I have to get home and I'm supposed to be cooking tonight. So I'm going to have to talk to my partner and figure out whether we can work something out around that. But we construct the story and we watch it play out in front of our eyes, if you will. We imagine it. And then what we do, and this is the part that we're least aware of, is we react to it emotionally. We react to it with just unbearable anxiety and worry. And then we decide, you know what, I just can't do it. Or we decide that we're really excited about it. We have these thoughts of really learning some new information, getting to talk to some people we've been meaning to talk to. And we imagine all of that. And there's positive emotions that come up. And we say, okay, I'm going to make it work somehow. So what are we doing? We're taking a current concern. We're imagining a future scenario that might solve that problem, solve that concern. We're watching our own emotional reaction to that scenario, and then we're deciding we'll do it or we won't do it. And that's what the brain does when we dream. It takes an ongoing concern some unfinished business. It doesn't have to be something big. It can be something remarkably small. You might have passed someone on the street who looked like they might be homeless, but you don't know. And you're curious. You sort of walk away saying, I wonder if she was homeless. And that's all. It's just a question that wasn't answered. And so your brain, as you're asleep, identifies this as an unfinished question. It goes and it looks for associations to that image and to that concept of homelessness. And it constructs a story. And then it plays out that story. And you, the dreamer, are almost always in that story. And you react emotionally within that story. And based on that reaction, your brain says, okay, relevant, useful association, and literally strengthens the synaptic connections between the recent memory and the older association, so that that association will be more likely to come up in the future when the triggering memory is recalled. Now, why does it have to dream about it? If you read Antonio, I've paused.
Damasio?
What's his? Damasio, right. If you read Antonio Damasio's book, The Feeling of What Happens, Damasio basically argues that consciousness is a gimmick that appeared at some point in evolution, which gave organisms the ability to do exactly what I'm describing, to create an imagined scenario and let it play out, to imagine how something might happen, to plan, if you will, for the future. And he says that the way you do that is you create the scenario and you monitor your emotional reactions to it. He's done work with people with calcified amygdalae who basically have dysfunctional amygdalae and cannot have emotional reactions to things in the way that normal people do. And they can't even make simple decisions that you would not call emotional decisions. I mean, for us scientists, we think our decisions are rational. But they may be rational in one sense, but in the end, they're always driven by an emotional response. We either say to ourselves, I like that, I'm going to do that, or I don't like that, I'm not going to do it. Or we say, I'm not sure about that, I have to sleep on that one. So that's how the brain evolved to perform this incredibly powerful function of imagining future scenarios. I mean, for a scientist, that's what we do par excellence. We imagine doing an experiment. We imagine how it might turn out. We imagine what that would mean. We then imagine what experiment would follow that and how this leads us to greater knowledge about the world. We couldn't do that without consciously imagining and emotionally evaluating different scenarios. And what dreaming does at night is it lets that process go into hyperdrive and look at these much more distant and unexpected associations. It allows us to be much more creative in our evaluation of possible outcomes of different types of events and of the usefulness of different types of associations. And again, the physiology of sleep, of the dreaming brain, is different from the waking brain in another way. In the waking brain, when we go through these imagined scenarios, we get to the end of it, we have that emotional feeling about it, and we make a decision.